Okay, here's another slope of a secant function generator. The only difference is in this case, as opposed to having a fixed x value like you had in the other problem where you're doing the average rate of change, in this one it's any two x values you want, where your first value is x and the second one is h away. So there'll always be a distance h away between those two. So notice that this is really just the change in y over change in x, where our first x value, our first value x value is x, and then our second x value is h away from the original x. So therefore this is the difference between our two function values, our difference between our two y values, and here is our two x values, where our first one is x and our second one is x plus h. And notice that when you subtract these two, you just get h. So we always just leave it in this form right here. So we'll look at an example where we have a function 3x squared plus 4x, and that we want to determine the function that will generate the slope of any secant line that goes through any 2 points on the function, x or h. And in this case, we'll actually use 2, and then our h value, which is just some distance away from 2, where it could be a half away, 0.1 away, 0.01 away. So let's just take a look at the visual here. Here is our function right here. Where'd it go? 3x squared plus 4x. Here is our secant line in this thin blue one here that I have drawn in. And this function right here, which is another form of this function right here, it's just that in Geometry Sketchpad I needed to use some additional variables to make it work. So just imagine that it says take an x value, subtract the two function values, where one function value is x and the other one is x plus h, and your denominator is h. So that's the same thing we have here. So notice this right here, 2.74, that is the distance between a and b. So the distance between the two x values is 2.74. Here's our function, or our ordered pair for b. It's not really imperative to our calculation, but I thought I'd just show it to you to should be clear to you. And then here's our initial x value, which is x sub a, which is the x value of a. And then here's the ordered pair. So it doesn't matter where our a and in this case our b value is, but really what is b? B is h away from x. Like we have here, here's our x plus h is our second value, our first value is x. So in this case, this right here is our b x sub b, and here is our x sub a. And that the h is equal to x sub b minus x sub a, where it's the distance between the two x values. So this is just the best way I could make it look using the Geometry Sketchpad. So here's our h value. So you want to focus on this, and just notice as this gets smaller, what happens to our slope value. So as of right now, we have our x value is at 1.9. I'm going to make that at 2, so I'm going to pause the computer for a minute. So here we have our x value at 2. Which is 20.1, which is an approximation, because if you plug in 2 right here, you're not going to get 20.1. So that's just an artifact, or the Geometry Sketchpad not doing what I really wanted to do. But let's imagine that that's at 20. And so therefore the slope between a and if I go h away from x, which is 2.66, so therefore if I go to the right 2.66 and then find that corresponding x value and function value and make the secant that connects those two, the slope of that secant will be 20.41. So if I want, I can move this point anywhere I want to, and notice that my slope of the secant value changes and the distance between the 2 points changes. Now it's at 2.05, so that means my x value is at 2, and then my second x value, which is h away from x, is at 4.05, or it rounded it to 4.1. So therefore, if you add these two, that'll get you your second x value. So I can move this point wherever I want to, and it doesn't matter, as opposed to the previous formula that we looked at, the average rate of change formula. Your initial x value had to stay the same. So I can move my initial x value if I want. I can move it up to 3, or approximate 3, it gets close to it without wasting a lot of time. So if I wanted to, I could move my x value to 3, and then I'll just get different secant slope values. And again, I can change b to make b to be really close, or my h value to be really small. And just notice to what happens to my secant line. Well, initially this genuinely looks like a secant line, where you can see a little space in between the secant line and the function. And obviously as I move these two closer to each other, what happens to my secant line, well, is look at the distance between the two of them is very small. Well, if I make the distance between them is, I don't know why that happens, the distance between the two of them is really small, what happens to my secant line, it ends up turning into, looks like a tangent line. Or if my distance between my two x values is 0, so therefore I'm just really finding the equation of the secant line that goes through x equals 3, and that's it. It looks like we have a tangent line, and that's exactly what we have. So if the distance between the two of them becomes very, very small, or namely 0, our secant line turns into a tangent line. So again, I can move this point A wherever I want it to be. It doesn't really matter, and I get different slope values. And again, I can use B. Again, what is B? Is just some distance away from x. So therefore, in this case, the distance is 6.86 away. I can move this point anywhere I want it to, and it doesn't matter. I'm allowed to do that if I use this formula, the difference quotient formula. So let's use the difference quotient formula to figure out the slope of any value, the slope of any secant line that goes to this function, given some x value, and then some x value that is some distance away, which in this case is, current situation is 2.92 away from 1.38. We'll do much nicer values. We'll do x is 2, and our h values are 0.5, 0.1, and 0.03. So if we have a new formula here, so let's just write out what f of x plus. So if f of x is equal to 3x squared plus 4x, that means f of x plus h is equal to 3x plus h squared plus 4 times x plus h. So wherever I see x, I'm going to put x plus h. So here's the beginning part of my formula, and then here's the second part. So the slope of my secant, this is another slope of the secant generating function, just a different form, is equal to 3x plus h squared plus 4x plus h minus the quantity 3x squared plus 4x. I'm going to put that all over h. So I'm going to square this right here. So this is 3x squared plus, when I square this, I get 2xh plus h squared. Plus, I'm going to distribute this 4x plus 4h, and I distribute this negative 3x squared minus 4x all over h. I distribute this 3. I get 3x squared plus 6xh plus 3h squared. And I just write these terms out here. 4x plus 4h minus 3x squared minus 4x all over h. Sorry about that. Actually, we can just delete that. I don't really like that. Oh, it went away. That's a little bit better. All over h. Notice my non-h terms cancel. So 3x squared and 3x squared and 4x cancel. I'm just left with terms and terms that are in terms of h, with redundancy. And you want that to happen. If you don't have terms that have h in them, then you made a mistake. So I'm just going to squeeze in over here. I should have plenty of room because there's not much left. So the slope of my secant is 6xh plus 3h squared plus 4h all over h. And notice everybody has an h in them, so I'm going to divide h into all three of these. So my slope of any secant line on this function, 3x squared plus 4x, is going to be 6x plus 3h plus 4. So this will generate the slope of any secant line on this function, given any x value and any second x value, which is h away. So let's scroll down here. And if this is my definition, if my x value is 2, then I want to use my h value is 0.5. So the slope of my secant at x equals 2 and h is 0.5 is going to be 6 times 2 plus 3 times 0.5 plus 4. I already calculated this out, so I'm just going to write this down as 17.5. And we'll look at that right now. So if x is 2, I'm going to pause here. So notice here that the distance between x sub b and x sub a, so this is my h value, is 0.5, and my initial x value is 2. So here is our initial x value, and here is a second x value, which is 0.5 away from our original one. So notice it's 2 and 2.5, but notice we never reference 2.5. We just use the h value because that's what our function is in terms of. Our function is in terms of an x value and an h value. So the best that I can get using this function here, which is the same thing that we have here, except it's written in using the formula, the original formula. It's written in this form up here. That's how I've written it. Gives us 17.52. So it's just that this is going out to more decimal places. I can't get it to be exactly 17.5, but it is exactly 17.5, but I can't get this point to be at the exact right correct spot. So this is our h value right here. Here's our initial x value. When we plug that into the big formula, unsimplified formula, we get 17.52. Let's just pretend that's 17.5. And when we use our slope of the secant function, we get exactly 17.5. So our second one is we want to do x equals 2 again, but we want to do 0.1 away. So the slope of our secant at x equals 2 and h is 0.1 is equal to 6 times 2 plus 3 times 0.1 plus 4. And courtesy of my calculator, that is equal to 16.3. Let's look at that on the graph. So in this case, it looks like A and B are almost right on top of each other. You can't really tell the difference between the two of them, but you can see them, but the distance is really small. How small? 0.1 away. Notice our initial x value is still equal to 2. And according to this, we get a slope value of 16.31 of this secant line, and we got 16.3. So again, that's just the best I could do without spending hours with moving the points back and forth. So my h value is 0.1, or the distance between the 2 points is 0.1, and my initial x value is 2, and we're on the function 3x squared plus 4x, and this is a secant line that we've drawn. How do I know it's secant? Because it goes through 2 points. Our final calculation is the slope of a secant when x equals 2 and h is 0.01. Notice that my h is getting smaller and smaller. I'm choosing that on purpose. So 6 times 2 plus 3 times 0.01 plus 4, we get 16.03. So let's look at the graph. So notice in this case, you really can't tell the difference between A and B because they're so close to each other. They're only a distance of 0.01 away. We're still at the x value 2 just because we decided to choose that one each time and just move our point closer and closer and closer. And notice in this case, it gives us that the slope value is 16.4. Well, we actually calculated it's exactly 16.03. Again, this is just an approximation according to the graph and the points. You just have to move the points a little bit better, and I could get that to be 16.03, but that's a lot of time. So therefore, if these points are almost on top of each other, it looks like the slope of this line is 16.03. And finally, if I put the distance between the 2 points as being 0, that means they're right on top of each other. So notice that A and B are both at the same ordered pair. According to this calculation, it looks like the slope of this line, which used to be a secant line, is no longer a secant line because it doesn't go through 2 distinct points. It goes through 2 points, but they're both the same. So therefore, it's really just intersecting 1 point on the curve. So when a line intersects a function at only 1 point, it changes its name from a secant and turns into a tangent. So therefore, what would the slope of this tangent line be? Looks like it would be 16.01. It's actually 16. That's just an artifact with having a hard time with moving these points to be in the exact spot. This number is exactly 16, so that leads us into the next question. What happens with the slope of the secant line as h approaches 0? So as h gets smaller and smaller and smaller, which in this case as it gets really close to 0, what happens to the slope of that secant line? Well, it ends up looking just like 16. And the last question is, what is the equation of the secant line when x is 2 and h is 0.01? Well, we know the slope of this secant line when x is 2 and h is 0.01. That is equal to 16.03. The only question is, what is our function value? Well, our function, I've already forgotten, is I think 3x squared plus 4x. Yep. So we want to do 3 times 2 squared plus 4 times 2. So this is 3 times 4 plus 8. So this is 12 plus 8, which is equal to 20. So using our point slope, we get y minus 20 equals 16.03 x minus 2. So I get 16.03 x plus 32.06 plus 20. That's a minus, sorry. Plus 20. So the equation of my secant line that goes through those two when h is 0.01, not when h is 0, is equal to negative 12.06. So there's the full process of looking at the second formula that generates the slope of secant lines. It's also known as the difference quotient as opposed to the average rate of change. Here's the equation of the secant line, and here's a slope of different secant lines given x is 2 and our h value is different values.